Hi boys and girls, this is lecture 6.3. The topic, the natural logarithmic function, integration, and this will be part 2 of our discussion. To master techniques of integration, you must recognize the form-fitting nature of integration. In this sense, integration is not nearly as straightforward as differentiation. Differentiation takes the form, here is the question, what is the answer? Whereas integration is more like, here is the answer, what is the question? Thus, we become detectives of a sort, examining the integrand for clues, which will help us determine the best technique for integrating. Here are some guidelines for integration. The first guideline, learn a basic list of integration formulas. This would include integrals of your basic trigonometric functions, natural log of x, e to the x, the power rule, etc. It's always handy to have a list at hand when we are examining the integrand for clues. Guideline number 2. Find an integration formula that resembles all or part of the integrand, and by trial and error find a choice of u that will make the integrand conform to the formula. This will be where you're using a u-substitution to restructure the integrand into a form that will allow you to integrate. Guideline number 3. If you cannot find a u-substitution that works, try altering the integrand. You might try a trigonometric identity, multiplying or dividing by the same quantity, adding or subtracting the same quantity, or long division. Be creative. And guideline number 4. If you have access to computer software that will find antiderivatives symbolically, use it. Our graphing calculators will find definite integrals, and we will be learning how to use them for that purpose. All right, let's put on our detective hats and get to work. We're being asked to solve this differential equation. Essentially, this is just a fancy way of asking us to take an integral. Let me show you what this looks like. We have dy dx equals 1 over x natural log of x. And if we multiply both sides by dx, we end up with this arrangement. dy is equal to 1 over x natural log of x dx. Well, solving the equation means to solve for y. So of course we would be integrating both sides of this equation to get y equals, and of course this integral will be the original function. But let's take a few moments to examine the integrand now. I see that natural log is in the denominator, and I might be tempted to let that be u, but I'm a little confused by the fact that there's also an x down there. However, let's just explore this possibility. What if u is natural log of x? Then du is 1 over x dx, which is exactly what I have. It's just unexpected because since it's 1 over x, that x drops to the denominator with our u natural log of x. We could rewrite this as 1 over x dx over natural log of x. Now this looks more like the du over u pattern. Essentially, however, we have discovered the technique for integrating. It is a du over u pattern, so it will be a natural log integral. So this is going to be the natural log of u plus c, but of course you need to replace u with the original substitution, which would give us y equals natural log of x plus c. With the log rule, we are able to complete the set of basic trigonometric integration formulas. So far, we're only able to integrate sine and cosine because those are direct derivatives of trigonometric functions. But using the log rule and trigonometric identities, we'll now be able to integrate tangent, cotangent, secant, and cosecant. Let's start with tangent. The trigonometric identity that we're going to use is the fact that tan x equals sine of x over cosine of x. So let's rewrite this integral as the integral of sine x over cosine x dx. We're going to let u equal cosine x. Then du is negative sine x dx. which is pretty much what we have in the numerator. It's a positive sign x and it needs to be negative, so we can add that -1 there as long as we compensate by multiplying by a -1 on the outside of the integral. Now this is a du over u pattern, which means we can integrate accordingly. This is going to be the negative natural log of cosine x plus c. In order to integrate the secant function, I'm going to use an unusual technique, multiplying and dividing by the same quantity. This technique can be added to your growing list of techniques for integration. I'm going to rewrite this integrand as a fraction, secant x over 1, and then I'm going to multiply it by this quantity, numerator and denominator, secant x plus tan x. And of course we cannot forget dx. When I distribute secant in this numerator, here is my transformed integrand. Secant squared x plus secant x tan x now is going to be over secant x plus tan x, and of course dx. Now this integrand is transformed into a du over u pattern. If we let u be secant x plus tan x, then du is going to be the derivative of secant, which is secant x tan x, plus the derivative of tangent, which is secant squared x dx, and that's exactly what we have in the numerator. So this little technique that we use transformed secant x over 1 into a du over u pattern, which means that we can now integrate. This of course is going to be the natural log of u plus c, but of course in our final answer we replace u with the original substitution, which means we'll get natural log of secant x plus tan x plus c. So here is the list of the integrals of the 6 basic trigonometric functions. The integral of sine and the integral of cosine are joined by integral of tangent, cotangent, secant, and cosecant. In this last example, let's find this definite integral involving trigonometric functions. Find the integral from 0 to pi over 4 of the square root of 1 plus tan squared x dx. Well, remember that 1 plus tan squared x is equal to secant squared x. That is one of the Pythagorean identities. So we can rewrite this as the square root of secant squared x dx. And of course the square root of secant squared will simply give us the integral from 0 to pi over 4 of secant x dx. We know that that's going to be the natural log of secant x plus tangent of x, and that's going to be integrated from 0 to pi over 4, which means we'll have natural log of secant of pi over 4 plus tangent of pi over 4 minus the natural log of secant of 0 plus tangent of 0. Continuing to simplify, we're going to get natural log of the square root of 2 plus 1 minus natural log of 1, which is approximately equal to 0.881. That's it for today's lecture. The art of counting, not just for fingers anymore. God bless you, boys and girls.